Today's section we will be seeing about how to connect a switch and send some data to the 8051 ports. So before going to that explanation, what we have seen in the last class is, if you look at the summary here, we have seen how to send a value to 8051 port, whether it is the complete port 8 pins together, we can send some data, or a particular pin of the 8051 port, any individual pins also. So we have seen how to send a value as well as to the port as well as to the pin. Also we have seen how to read a particular pin or read a port also, and how to change the values based on the input, how to change the values to a particular pin or a port. And we have also seen how to generate a square wave, and a square wave will be having a duty cycle of 50%. So if the duty cycle is 50%, we know that we can use the same delay subroutine which creates the delay equivalent delay. Now when it comes to a different duty cycle, like in rectangular pulses, we will be having different on time and off time. In such cases, we have to use two different delay subroutine. This is what we have seen in the last class. The first example today. So what we will be seeing in the first program is we have a switch which is connected to P1.7. We have a switch connected, and based on the status of this switch, we will be sending some data. The data what we are sending is the value y, that is for yes, and the value no, that is for the value n, that is for no. So this is the program. So remember, we will be sensing the P1.7 and we are connecting P1.7 to a switch, and the switch, if the switch is pressed, this P1.7 will become 1. So that's a condition. When the switch is pressed, P1.7 will become 1 or logical high, and if the switch is not pressed, then this pin P1.7 will become logical 0 or low. So this is the switch condition, and based on this condition we will be sending, if the switch is pressed, we will send yes or y. If the switch is not pressed, we will send no or n. So this is the program. So now I will explain this. We are sending yes or no, but remember, yes or no are alphabetical or characters. Now when we are sending yes or no to this port, what we are really sending is some hexadecimal value. So hexadecimal value for which is equivalent to yes, and hexadecimal value which is equivalent to no. That's only what we can send it to a port. So naturally we will be using the ASCII equivalent of yes and ASCII equivalent of no for sending this yes or no to the port 2, and ASCII equivalent of yes is 59, hexadecimal 59, which is shown here, and ASCII equivalent of no is hexadecimal 4e. But anyway, we really need not worry about what is the hexadecimal value. If you write in the program with a single quote y, this will be considered as the ASCII value. This the corresponding ASCII value. Suppose if you write something like P2 is equal to, then in the quotes if you write y, then what will be in the port P2 will be nothing but 59 hexadecimal. Similarly, if you write P2 is equal to, I mean there is no equal to in the assembly level program, but for the explanation I am writing P2 is equal to n. If you write, then we will be getting this value for E in the port 2. So this is how we will be sending a character yes or no to the particular port. Let us see how this program works. So as I explained in the circuit diagram, we have connected a switch to P1.7 and we are checking the status of that switch and send a letter no if the switch is 0 to a port P2, and if the switch is 1, send a letter Y to the port P2. And if you look at the program as you see, it is a very small simple program. So the first thing what we will do is we will have to read the content of the pin. So if we need to read the content of this pin, this is the pin which we are going to read the content. So this pin has to be configured as an input pin. So when you wanted to configure this input, because switch is an input device and this pin has to be configured as an input pin. So in order to configure this pin as an input pin, we will have to send a 1 to the pin. So that is why we are setting the P1.7. Set bit P1.7 is for making this P1.7 as an input pin. And what next we will do is we will check the value of this pin. So this is actually P1.7. It's not P1.2, it is P1.7. okay, so there is a small mistake in this point. Okay, so you have to do one thing, you have to check this P1.7, and if this P1.7 bit is 1, so we have written here JB P1.7, that means jump if P1.7 is 1, right? So yeah, so if the P1.7 is 1, what is that we need to do? If the P1.7 is 1, that means the switch is pressed, so we have to send the letter Y to the port. Yes, so what we will do is if this bit is if P1.7 is 1 in this line, then it will jump to this label over, and that label is here, and in that label it is written move P2 comma #Y. So it is clearly explained. If this bit is 1, so when this P1.7, if it is 1, then this P2 will be the ASCII equivalent of the letter Y. So the ASCII equivalent of letter Y is can be sent to P2 just by writing this line move P2 comma immediate data hash and the ASCII value. So you must remember to put this quotes. Okay, without putting this quote, this will give an error. So when you put the quote, it will convert this Y into an ASCII value. So it is as if you are writing that particular ASCII value. What is the ASCII value of Y? It is 59, right? So the moment you say that move P2 comma hash, then in quotes Y. When you write like this line is same as you write move P2 hash 59H. So it's the same thing is being done using this line. So that is why you have to make sure that these quotes are mentioned. So if this bit is 1, then P2 will be having this Y. And again, what we have to do is we have to check the value of P2 because it is keep on continuously checking the P2. So what we will do, we will jump back to this line. P1.7 is 1. It will always jump to this over this particular label, and it will send P2 as always Y. It will keep on doing as long as this P1.7 is 1. So when this P1.7 is 1, the switch is pressed. So when the switch is not pressed, that means if P1.7, if it is 0, then it will not go to this over, that is the label. It will directly execute the lines which is below this instruction, that is these two lines. So what is this line does? It is simply sending no, the letter N to P2. So the letter N, so as I mentioned earlier, we will be writing move P2 comma hash N for N in quotes to send the ASCII equivalent of N, and the ASCII equivalent of N what we have seen is 4E. Yes, so 4 is the ASCII equivalent of N. So P2 will become 4E in this in this instruction, and so this will be happening only if P1.7 is 0. So this is a very simple program which will be sending the letter N or P to P N or Y to the port P2, and this sending will be depending on the switch status where the switch is connected to pin P1.7. Writing the program is using a carry flag. So here we have seen we have directly checking the content of this P1.7 using this JB instruction. So JB P1.7 is the key instruction which checks the switch status. Now once it comes to another style of writing this program which is written here, again the same program, it will check the switch status where the switch is connected to P1.7, and it will say N or Y to P2 depending on the switch condition. But here we are using not this JB instruction, but we are using JC instruction. So we will be using a JC instruction here. So what we will be doing is, instead of writing, so I will just write only that part here. Instead of writing JB and the pin P1.7, what we will be doing is P1.7. What we'll be doing is, we will be taking the content of P1.7, we will move that value to the carry bit and check the content of carry. So these two instructions together will replace this one instruction here. That's all the difference. So if you see, we have two instructions, move C comma P1.7 and then JC, whereas here we have only one instruction, JB, which is checking the content status of P1.7. So that's only difference. So again, how this program works? This program works in such a way that if the switch is pressed, if the switch is pressed, then you know that P1.7 will be high. So high means a logical 1, so carry will become 1. So if there is a carry, jump if carry over. So if there is a carry, it will execute this particular line, and in that line we have written as P2 as yes. Okay, this is what we have written. So that is if P1.7 is high. Now if there is no carry, that means P1.7 is low, then that means the carry is also 0. If carry is 0, what we have to write? We have to write P2 is equal to no. So this is the program, and this program will keep on executing till the continuously. It will keep on executing continuously. So these are the two styles of doing the same program. So the program is very clear to you, I believe. We have a switch which is connected to P1.7 and send the letter Y or N to this port P2 depending on the status of the switch. So with this, we will move to the last program which we are going to explain here. In our next example, we will be checking the status of a switch as we have checked in the last program. So we will check the status of this switch, and based on the switch condition, we will send whatever the condition of the switch to this LED. So we have the conditions like if the switch, if it is pressed, if the switch is pressed, if it is pressed here, then LED will be on, and if it is not pressed, if not pressed, then the LED will be off. So what we need to do? What we need to do is, like, if the switch is pressed, we will know that P1.0 will become 1, and we will send P2.7 equals 1. So when P2.7 equals 1, LED will be on. And if the switch is not pressed, then we know that P1.0 will become 0. And when this P1.0 is 0, this P2.7 also we will make it as 0 so that the LED is off. So whatever is the value of P1.0, the same value will be there in P2.7 as well as in both the cases, whether it is 1 or 0. So this is a simple program, but ultimately the application is switch is connected to the microcontroller, and based on the switch status, LED is switching on or switching off. So this is the circuit diagram. So let us see the program. Let us see the program. Now the program is this one. So here, as we have mentioned, the switch is connected to the P1.0 and LED is connected to P2.7. So take this, get the status of the switch and send it to the LED. That's all, very simple. And what we are doing is, first we have to make sure that the switch is connected to P1.7. So we have to read the switch status. So P1.7 must be a input port. So we will make this P1.7 as an input port by writing a 1 to P1.0. So we will set this P1.0. Let us see the program. So as we have mentioned here, the switch is connected to P1.0 and this LED is connected to P2.7, and seeing the status of the switch, the same status is sent to the LED. So the switch is connected to P1.0. It's mentioned as P1.7, right? Okay, so this is nothing but P1.0. Okay, so the switch is connected to P1.0. So as we have seen that P1.0 must be configured as an input port, because this is the we are reading the switch through this pin, and in order to do that, we will write 1 to P1.0 by setting this bit and configure this pin as an input pin. And what we will do is, then we will read the 1.0 value, moving that value to the carry bit. So whatever is the switch status is now available in carry. So if the switch status is, if the switch is pressed, then P1.0 will be 1, and hence carry also will be 1. And the same carry value we are moving to P2.7 here. So here P2.7 also will become 1. So what happens is, here the switch is connected in P1.0 and here the LED is connected. So that means if the switch is 1, LED is 1. That means if the switch is pressed, LED will glow. And if the switch is not pressed, then you know that P1.0 will be 0 and the carry also will be 0 because of this line, and the same carry will be moved to P2.7. So P2.7 also will be 0. That means if the switch is not pressed, here the switch is not pressed. Okay, so that means LED is 0. That means LED will not be glowing. So this is the program to write the status of a switch to an LED, and we will keep on doing this continuously. Okay, so there are few things which is written here. The instruction move P2.7 and P1.0 is wrong, right? So that means you already know this. That means we cannot write instruction like move P2.0 comma hash 00hy, because this is a bit and this is a byte. So a byte data we cannot move to a bit, whereas what this line says that, and what this line says is we can write move p2 comma hash 00 hash. Why? Because 00 is a byte, whereas p2 is also a byte. So byte to byte is possible, but byte to bit is not possible. So this is what these two blocks written inside. So with this, we will conclude the complete examples of these modules, and we will go to the summary section of this entire module. So to summarize this module, if you remember, we have completed the last 4 video lectures. In that, the first thing what we have seen was about the stack. So what is a stack? That's what we have seen in the first video, and in that we have observed that stack is nothing but a memory itself, and we have got stack pointer, and the stack pointer will hold the address of the stack, and stack is generally the default value of the stack is stack pointer is 07, as hence the stack memory will be starting from the internal memory 08 onwards. That's a default case. This is what we have seen about the stack. And in this process we have also seen the instructions which deals with the stack, that is push and pop instructions. Also we have seen the effect of call and return instruction on the stack, as well as the stack pointer, as well as the program counter. So in this process of explanation, we have seen what is program counter, which is holding the address of the next instruction to be executed. So the program counter holds a 16-bit address, and in any looping or jumping instructions, basically the content of this program counter is getting changed, and how exactly the program counter values are getting changed when we call when we use a push or a pop instructions, we have observed. Also we have seen how this program counter is getting changed when it comes to calling a subroutine using call instruction as well as return instruction. So this is what we have seen in the about the program counter. And then we have gone through the concept of subroutines. In subroutines, we have seen that what is the need of a subroutine, and why we will be using the subroutine. In subroutines, we have seen why we will be using subroutines, and what's the purpose or what is the need of a subroutine. We have seen that when there are some set of programs which is to be executed frequently. So when we have to execute certain set of instructions frequently, we will be using it as a subroutine, and we will call the subroutine whenever we need to execute those frequent programs. And after the subroutines, we have seen some of the example programs which involves the loops. So we have seen the programs which is involving loops in a few examples, and we have seen that instructions like such as CJNE or DJNZ, all these kind of instructions, how are we using in creating a loops. And also we have seen how to use the counter to perform a loop on a finite number of times. Also we have seen that how to have this loop for a minimum number of times, or if you want more number of times, if you wanted to loop a particular program, how we will create a loop in loop instruction, all these things. Okay, so after that we have seen about some programs. We have seen some example programs which is involving loop subroutines. So we have written some programs which is involving subroutines, and also we have analyzed how the PC, how the stack pointer and the stack etc. is changing with respect to the subroutine programs. With this, the first section of the module 3 was completed. So the first section is up to this point, and later the next section is about the 8051 input-output ports. And in the 8051 input-output ports, we have studied in detail about port 0, port 1, port 2, and port 3. And also we have seen the port 0 will be requiring pull-up resistors, whereas other ports does not require a pull-up resistor. And we have seen by default every port is acting as a input port. That is the default case, and if you need to configure any port as an input port, we need to write 1 to the port pin, write high to the pin to configure that port as an input port. So to configure it as an output port, we have seen that we need to write 0 to the pin or the port. So this is with respect to the port. We have seen all these things, and we have seen how to read or write to the port, as well as how to read or write to the pin. And later we have seen some of the assembly level programs to read or write to the pin or the port. So we have seen few examples of reading a particular pin or reading a particular port itself. And also we have seen how to generate a square wave and how to create a square wave with a duty cycle or with a frequency of a specific frequency, how to generate a delay, how to generate a time period, all these things. And we have seen if it is a rectangular wave, that means if the duty cycle is more than 50% or less than 50%, then how we will be writing the program. We have seen for while generating a square wave. And at last we have seen some sample programs, which that is in the today's section. We have seen how to read the status of a switch how to read the status of a switch, and how to send a particular data to a port or a particular pin if that pin or port is connected to a peripheral or a devices or a circuit like LED, how to read the status and how to send the data to this peripheral or a LED we have seen. So these are the topics which we have observed in this module 3. With this module 3 topics are completed, and if you have any specific questions or anything, you can just access our Google Classroom and you can raise your questions there, and I will be definitely answering to all your queries. So thank you so much.